All right, let's go ahead and solve this problem. So we are talking about tidal volume with known minute ventilation and respiratory rate. So let's go ahead and read it. Calculate the average tidal volume for a patient who has a minute ventilation of 8 and a respiratory rate of 14 breaths per minute. Okay, so let's start out by figuring out our equation. So that equation is going to be tidal volume equals minute ventilation divided by respiratory rate. Let's plug in our information. Our minute ventilation is 8. Our respiratory rate is 14. Go ahead and divide that. What you will get is 0.571. Important to take note that this is in liters. So in order to plug that into the ventilator, we're going to convert that into milliliters. You do that by moving the decimal over 3 places. 571 milliliters. Now for this equation, it's most likely being used for a patient that is on pressure control ventilation. So you have the respiratory rate and you have the minute ventilation, but you don't have the tidal volume. Okay, let's move on to this problem. We're solving for inspiratory time with known tidal volume and flow. Calculate the inspiratory time when a ventilator is set at a tidal volume of 600 milliliters and a constant flow of 50 liters a minute. So we have tidal volume and we have flow. Let's figure out our equation for this first. So our equation is going to be Ti equals tidal volume divided by flow. Let's plug in our information. Our tidal volume is 600 and our flow is 50. Now the first thing that we're going to have to do is we're going to have to convert these. We're going to have to convert the tidal volume that is in milliliters into liters. And we're going to have to convert the liters per minute into liters per second. Okay, so for our tidal volume, we're going to convert that from milliliters into liters by moving our decimal to the left 3 spaces. So now that is 0.600 liters. And for flow, we're going to divide it by 60 because there's 60 seconds in a minute. And that's going to come out to 0.83. Okay. So now we have it in measurements that we can actually solve for here. We'll just do that math and plug it in. 0.600 divided by 0.83. and your TI is 0.72. TI being inspiratory time with known tidal volume and flow. And this is something we would set on the ventilator. And for a normal adult, that's typically going to be 0.8 or 0.9. All right, let's move on to this problem. We are trying to figure out what the I to E ratio is with a known I time and respiratory rate. So let's jump in. Calculate the inspiratory to expiratory ratio when the inspiratory time is 0.6 and the respiratory rate is 25 breaths a minute. Our equation here is going to be, well, first we have to figure out what our expiratory time is. So that's where we'll start. So multiple equations really, but we're going to start with figuring out what our expiratory time is. Total cycle time minus inspiratory time. That's how we're going to figure out our expiratory time. So we do have to remember the equation for total cycle time, and that's going to be 60 seconds divided by respiratory rate. That's our total cycle time. So for this equation, that's going to look like 60 divided by 25. Our I time is 0.6. We'll plug that into the calculator, and what we're going to get is 1.8. Okay, so now we have our expiratory time. I to E ratio, our inspiratory time 0.6, expiratory time 1.8. As we're thinking about this, when we think about the I to E ratio, the I is always represented as 1. So what we don't know is expiratory time. To get expiratory time, you are going to divide E by I. We'll plug that into our calculator, and that is going to be 3. So what we just did is we solved for our E in ratio form. Our answer to this problem is a ratio of 1 to 3. Okay, moving on to the next problem. We're trying to get expiratory time with a known I time and respiratory rate. So kind of like the last problem we did. Let's read our problem. Calculate the expiratory time when the ventilator frequency is set to 15 and the inspiratory time is 0.9. Our equation is going to be expiratory time equals total cycle time minus I time. So we have to remember, so it's an equation within an equation. What is total cycle time? 60 seconds divided by respiratory rate. So let's plug in our information. Our respiratory rate here is going to be 15, and our inspiratory time is 0.9. We put that into the calculator, and our answer is going to be 3.1. So our expiratory time is 3.1 for this problem. All right, ideal body weight, everybody's favorite. Now there are lots of equations that can get you to an answer to figure out tidal volume, which is what we're doing with this ideal body weight. We are trying to set up a ventilator and set tidal volume for a patient based on ideal body weight. So let's read the problem here. Calculate the tidal volume settings for a 6'2" male ventilator patient with normal lungs. We have normal lungs here, so let's remember our ranges. So for normal lungs, our range is 6 to 8, and for, we'll say, restricted lungs or ARDS, 4 to 6. I told you guys to remember the number 7 for normal lungs and the number 5 for restricted or ARDS lungs. Okay, so what do we have here? What is our ideal body weight equation? The one that I like is going to be 50 kilograms plus 2 times inches over 5 feet. Our patient here is 6'2". Now, this is where it gets tricky when you're over 5 feet. You have to remember that that's, when you're 6 foot, that's 12 inches from 5 foot to 6 foot. And then you're adding that as well. That's going to give you 14 inches over 5 feet. So let's plug that in. So 50 kilograms plus 2 times 14. So that comes to 50 plus 28. This patient's ideal body weight, and this is in kilograms, is 78 kilograms. No need to convert it into anything else. Kilograms. These ranges over here are in kilograms or milliliter per kilogram. So we have kilogram and kilogram. We're saving some steps. Now, normal lungs. So this range and that number that I told you, number 7, is what we're going to multiply it by. So 78, and we're solving for tidal volume now. 78 times 7, and that's going to give you 546 milliliters. Now we can plug this into the ventilator and ventilate a patient. All right, we got another tidal volume equation. So we are trying to get set tidal volume using ideal body weight. Let's go ahead and jump in. Calculate the tidal volume setting for a 5'5" female ventilator patient with normal lungs. What tidal volume and respiratory rate should you set this patient on? Okay. So we'll want to check our settings by checking minute ventilation, but we're going to start with ideal body weight. Ideal body weight, 50 kilograms plus 2 times inches over 5 feet. I'll write our normal ranges over here again. So for normal lungs, we have a range of 6 to 8 milliliter per kilogram. I told you to remember the number 7. And then for restricted or ARDS, 4 to 6, I told you to remember the number 5. Again, milliliter per kilogram. So our patient is 5'5". So let's solve for that. 50 kilograms plus 2 times 5 inches over 5 feet. And that's going to be 10. So our ideal body weight is 60 kilograms. So from here, we're going to take our 60 kilograms and we're going to multiply it by, let's check the lungs. This patient has normal lungs. So we're going to multiply it by my favorite number for normal lungs, and that's 7. We're solving for tidal volume now. 60 kilograms times 7, again, milliliters per kilogram. And that is going to give us a tidal volume of 420 milliliters. So now we can set the tidal volume, but we want to make sure what respiratory rate should you set this patient on, right? So we're setting more than just one setting. So let's talk about the settings for a ventilator real quick. FiO2, tidal volume, we're in volume, respiratory rate, and PEEP. So we have a tidal volume of 420. Let's get the respiratory rate. The equation for minute ventilation, tidal volume times respiratory rate. So we're going to plug in our tidal volume. Now minute ventilation is in liters. Tidal volume that we have here is in milliliters. So let's convert. That's going to be just moving that decimal over. So now we have 0.42 times a respiratory rate of our choosing. So for normal lungs, well, normal respiratory rate, let's start there, is 12 to 20. Typically for normal lungs, we're going to set it between 14 to 16, depending on our tidal volume and what we're trying to do. So let's start with a respiratory rate of 14. So we'll plug that in to our calculator, and we are going to get a minute ventilation of 5.88. That is our minute ventilation in liters. Now the question is, are we ventilating this patient well? Normal minute ventilation is about 5 to 10. We're in between that range. So we are ventilating this patient, and this patient will ventilate on the settings that we have. So let's just go ahead and plug that 14 in there. Typically we start PEEP anywhere from 0 to 5. Very common is going to be 5. FiO2, nothing in this equation says anything about hypoxemia or low oxygen. We might start this patient at an FiO2 of 40. Titrate down if needed, keeping an eye on their oxygen saturations. So that is how we would calculate to set tidal volume and ensure the patient is being ventilated. All right, let's solve for desired FiO2 with known FiO2 and known PaO2. Let's go ahead and read this problem. What FiO2 setting should be set on the ventilator when the patient currently has a partial pressure of oxygen, PaO2 of 50, while receiving 40% oxygen, or FiO2, and the desired PaO2 is 90. So the patient's PaO2 is 50, we want it to be 90, but we're giving them 40% FiO2, or oxygen. Okay, let's start with an equation. So we'll say that D stands for desired. So desired FiO2 equals desired PaO2 times, we'll say K stands for known FiO2 divided by known PaO2. So let's go ahead and plug this in. Desired PaO2 is going to be 90. Known FiO2 is 40. And known PaO2 is 50. Super important to remember when you're using percentages, you have to change that into, that's right, a decimal. So let's not forget that step. We plug that into our calculator and we will get 0.72. That is going to be the FiO2 that we set our patient on to go from 50 to 90 in their PaO2. So the answer is going to be 72.